All right, welcome back, everyone. I hesitate to use everyone because there's two people in the room and one person online. But let's get started. We got 3 more chapters I'd like to get done before the end of the semester. 17, 18, and 19. 17 is on geometry. So let's get started talking about geometry. So we can have a point. We use the word point to describes a location in space. Is that it has no units and really no size. But we usually put a dot there to make the point visible. Pen, get rid of that. Point. Then we have a line. Is a infinite range of points in along a straight line, straight path. That's just like a definition for it. You all know what a fucking line is. This isn't rocket science. That's a line. It could have a bunch of points on it. And we can indicate a line several different ways. We usually pick 2 points on the line. So pick 2 points on the line. And do the following with them. If I go with like B and E, we put an arrow above it. The arrowheads indicate that it keeps going on forever. And I could label that line more than one way. I could call it BE like I did. I could call it AB. Those are 2 points on the line. I could call it AF. I could call it any two points, as long as it describes it that way. A line that does no arrowheads like this is called a line segment. That's how we distinguish between them. A line segment or just segment. And the labeling is very specific. Even if I have points on the inside, the line segment is labeled with the endpoints only. And there are no arrows on the thing that go above it. endpoints only are listed. You guys good with that? So two lines can interact in three different ways. One, they can cross or intersect at a single point. Like that. Option B is called they can coincide or lie on top one another. So I'm gonna maybe do this with one thick line, if I can, to indicate that underneath line. I put arrows on it. And then the other line is right on top of that way. That's not too bad. And option 3 is they never interact. Never touch. When they are like this, we call them parallel lines. And if this is line AB and this is line CD, we say line AB is parallel to CD. That's the parallel sign. Now, you're supposed to use a double-headed arrow. That's the traditional way of doing a line. I think it's easier to write it where you do this. And it only shows the top part. Because then the bottom half of the arrow isn't messing up your letters. This is a dead pin too. So you'll probably see me write the ladder one more. The points are considered one-dimensional. Let me go back and put that real quick. Points are considered one-dimensional or 1D. And lines are 2D. Or two-dimensional. Space in general is three-dimensional. And for geometry, we're not really doing anything with that as of now. Okay, there is one more, another two-dimensional figure. Is a plane. Or flat surface that extends indefinitely. In both directions. Kind of like the paper this is written on. If the paper went on forever. If it wasn't just 8.5 by 11, but it was a gazillion by gazillion. You know, it's like planet, just a flat surface that goes on forever. All right, I got some more terminology. So we've done lines that have arrows on both sides. We've done lines that have no arrows. Finally, we have the line that has an arrow on one side and not on the other. This is called a ray. A ray is a line with one endpoint, a starting point. Which is called the endpoint. So it only goes infinitely in one direction. And generally they call it something like this. With one arrow. When you get to well, you guys aren't taking that route, but for the students that do go into like engineering and shit like that, this symbol, this notation means something entirely different. It's the equivalent of the line. It's called a vector, and they don't put the arrows on both sides. But your book is. All right, so that's called a ray. So if we have two rays, that share the same endpoint. Make an angle. I'm gonna call this A, B, C. This book doesn't do it, but I know I'm gonna do it at least once by accident, so I might as well just embrace it the whole way. This is the angle. And I tend to call it theta. Theta, it's a Greek letter. The way the book is gonna write this angle looks like this. ABC, where you list the point in the point where it starts from in the middle. I could also call this angle CBA, but this is really just angle B. So there's two ways of really labeling it.
How do you pronounce that word? The angle? Yeah.
Theta. Theta. Or theta, if you're Greek. You should probably pronounce it theta. Now, this is a fun story. Has nothing to do with it, but it rhymes with theta. That is this word right there. Most Americans pronounce it beta. That's Americans. It's pronounced beta. It's the real way. And I was in grad school, and my teacher was from England, and he kept making fun of us anytime we say some American shit, that like you Americans and shit like that. It was good fun. But he said beta one time, and we had a student that was Greek. And she countered with, "It's beta, you ignorant English person." It was fucking fantastic. The reason why, and it makes sense, this is alpha. And if you say them together, alpha, beta, alphabet. So that's how I remember how to pronounce beta now. But there was a VCR, I mean, shit, you not remember it probably. The Betamax was the before regular VCRs, and it was called beta, and it was spelled like that. But it's beta. It was great. All right, back to the lesson at hand. Okay, so the point P or B is called the vertex. That's a side note. That's a side stuff right there. B is that. And the rays BA and BC are called the sides or legs of the angle. So this, we tend to rotate. We measure, this is called the angle measure. When the name of it is those names. Angle measure, like measures how much it rotates. So like you can't like, if you try to do it at different sides, it's not like measuring the length. I can't just take this and put a string on it and measure the length. It's really just how much it rotates. So we'll talk about rotation in a second. But these tend to be the one that counts. There is another angle that is shown here though. And that is this angle. This is another angle. Maybe we'll call that theta or psi. I think that's psi. This is also an angle. It sounds funny saying between two sides. Because like these don't like between looks like this side. But picture it more of like a book. So I can open the book and it makes an angle. And I can keep opening the book and have the book come all the way around and keep making the angle bigger. So I've made the angle so big that it now looks like this is the angle when really the angle is going all the way around. That's the idea. There's two angles there. Every single time, the angle that is meant is the inside one unless specified otherwise. This is the angle we will use unless specified otherwise. That book made a really good way of portraying that. I'm pleased with that. You guys ready for some more? I got a little bit more room. I can add it here. When we rotate like this, counterclockwise rotation. Is called positive rotation. And then clockwise rotation is negative.
You will think the other.
What?
You will think that it's the opposite.
Right. So how do we measure rotation? Rotation is measured by degrees or angle is measured two ways. But the one we're doing in this section and the next section is in degrees. And later on, we will talk about radians. But we will focus on degrees. Let's say I had two rays. Nope, better way of showing it. The actual alignment of a clock. It's 12 noon. So they're both pointed up. When the hour or the minute hand sweeps a full rotation around the circle. Complete rotation. Measures 360 degrees. That little floating O is the degree symbol. And you've seen it before with degrees Fahrenheit, degrees Celsius. It means a different context in temperature than it does in angles. But this is still the same word and they use the same symbol, which is nice. It's too bad they don't measure or do clocks like they started doing geometry. The whole, like, that clock was developed long after the information on how we deal with circles and angles was developed. And we start a circle here and rotate like that. You would think we could have made clocks that did the same thing. But instead we chose straight up to be, and it's only, it only seems funny because you're used to the clock going the way it does. If clocks went this way, then the whole like counterclockwise being positive wouldn't sound funny, because that would be the directions clocks go. But for some reason, some asshat didn't know shit about, whoever came up with clocks didn't know anything about mathematics, which is surprising because there's a lot of engineering behind a clock. So 360 degrees. If I only go 90 degrees for a quarter of a circle, this is called a right angle. And they put a square in the corner. Square in the corner. That's to indicate that it is in fact 90 degrees and not like 89.5 where your eye wouldn't be able to distinguish it. Or 89.9. These are also called perpendicular lines. These are perpendicular. When the line goes straight up, as it's doing right here, this is called a vertical line. And when it goes left and right, as it does here, that is called a horizontal line.
So what's called perpendicular?
Perpendicular is when they make a 90-degree angle. They make a cross. It doesn't have to be like that. It could be like this. But each corner is a right angle. Streets generally cross at perpendicular lines. A plus sign is perpendicular line. Generally, the notation for perpendicular is not a plus sign because, well, we use plus for addition. The notation for perpendicular is like part of a plus sign. So that's the indicator for perpendicular. Angles that are larger than 0 degrees, but less than 90 degrees are called acute angles. So if they're less than a quarter of a circle. If they go up to 180 degrees, 90 degrees, up to 180 degrees, these are called obtuse angles. I don't even think we call 0 an angle. 90 isn't called acute or obtuse, it's called the right angle. And an angle of 180 degrees. Is called a straight angle. Because it makes a straight line. I'm 4 pages into lecture notes and we haven't done any mathematical operations yet, have we? I think we should. I think we gotta slip it in somewhere. This is taking so much longer to go over these fucking all these rules. Ready for more? All right. So when we have two angles that make a 90-degree angle together. Like this whole thing is a 90-degree angle. And let's call this angle A and we'll call this angle B. Angle A and angle B are complementary. There is no I in this word complement though. Complementary. They add to 190. Not 190, 90. Add 90 degrees. So if we know, like say A is 30 degrees. Find the complement of A. Which in this case, the angle, the measure of B. The way you go about doing it is we know A plus B equals 90. We're looking for B. So if I subtract A over, I get B equals 90 degrees minus A. So if we apply this here, angle B is 90 degrees minus 30 degrees is 60 degrees. If A and B add to 180, they are called supplemental angles. A plus B equals 180. So B equals, just like we had above, instead of having 90 though, we have 180 minus A. So if A is 120 degrees, find its complement. Or supplement, find its supplement. We would do B equals 180 degrees minus 120 degrees equals 60 degrees. So if I have two angles. Let's call this ABC. And this is DEF. And the measure of the angles is the same. I'll call that theta, and this is also theta. Then these two angles, ABC, is said to be equal to DEF. When they have the same angle measure. They are equal angles. Every once in a while, you will see them called congruent angles. But I am not going to use it. I know the book will. We're going to use congruent on geometry when we have shapes. And I hate having a word for two different, the same word and the same sections, having two different, drastically different meanings. Not drastically different, but different enough. Okay. Jargon intention section coming up shortly. It's important, what I'm going to do here, I'm going to show a small picture of a variant of it. And then the one I'm going to do all the math with. Okay, so the red line here on both images is called the transversal line. Transversal line crosses more than two lines. On the left one over here, the blue lines are parallel. If they don't appear that way in the sketch, that's because I didn't use a ruler and just draw on both sides. Over here, they are not parallel. But I'm going to label the angles the same. I'm going to call this 1, 2, 3, 4, 5, 6, 7, 8. It's over here. 1, 2, 3, 4, 5, 6, 7, 8. These represent the angles. Okay, so angles opposite each other. Where two lines meet. Are called vertical angles. Or vertical angle pairs. So angle 1 and angle 4 meet that criteria. Angle 2 and angle 3 meet that criteria also. So does angle 5 and angle 8. And angle 6, angle 6 and angle 7 also do that. Angles that touch where two lines meet are called adjacent angles. So just focusing on the first 4, angle 1 is adjacent to angle 2. Angle 2 is adjacent to angle 4. Angle 4 is adjacent to angle 3. And angle 3 is adjacent to angle 1. They are next to each other. This is true for either picture. Both of these terms are true for either picture. So they have something called interior angles. This is also true for both pictures. In fact, I will tell you when it's not true for both. Interior angles are on the inside. In this case, that is angles 3, 4, 5, and 6. Those are called the interior angles. Exterior angles. Are on the outside.
So it will be 1, 2, 7, 8.
1, 2, 7, 8, exactly. What?
I think I kind of remember where we're going with this. I think.
I don't know how to put this in words, so I'm just gonna show them. I'm sure the book has a verbal definition. They're called corresponding angles. Angle 1 and angle 5 are corresponding angles. They are on the top left. One of the top left angles for where the transversal line crosses. Angles 2 and 6 are corresponding angles. And
What
so
about 3 and 7?
3 and 7 is another. And what's the last one?
4 and 8.
4 and 8. Well, I think I can squeeze in. I probably can't. I'm going to try. Alternate interior angles. This is a word or phrase. Alternate interior angles. So interior means they are on the inside. And alternate means they basically don't touch. So angles 3 and angle 6 are alternate interior angles. Angles 4 and angle 5 are alternate interior angles. Alternate exterior angles. Have to follow the same pattern. We don't want to have them there on the opposite side of the transversal line. So angle 1 and angle 8 are alternate exterior angles. Angles 2 and angle 7 are alternate exterior angles. This is true for both pictures I've drawn. I can't get out any. It's true for both pictures. That's the jargon. You just want like a 5-minute break? You're already picking up your phone as soon as I stop.
No, just my son was. That would bought me up that is gonna expire on May 4th. Sorry.
It's okay. It's like, but I mean, it's been an hour. I know we could take a 5-minute break. I don't mind. So let's take a look at that example where I had 2 parallel lines with a transversal line. And I will relabel the angles all the same so they match up with the wording we had before. So when the lines are parallel, for this setup with parallel lines, and they have to be parallel. If they are not parallel, the following does not apply. One, corresponding angles are equal. Angle 1 has the same value as angle 5. Angle 4 has the same value as angle 8.
So then 3 and 7 are the same.
3 and 7 apply, yes. 3 equals 7. And 2 equals 6. Number 2. Vertical angles are equal. I think this is a stupid word. I think a better way of describing it is called opposite angles. But even that doesn't work, it only works in this side. We tend to use opposite in right triangle trigonometry, so I hate saying that, but they are like opposite each other. So they are equal. So 1 and 4 are vertical angles. Angle 1 equals angle 4. Angle 5 equals angle 8.
You want 3?
2 and 3 go together. And 6 and 7 go together. So if we put these two together, if we put 1 and 2 together. The following angles are all equal. Angle 1 equals angle 4 equals angle 5 equals angle 8. One and 5 are corresponding, and 4 and 8 are corresponding, but we know 1 and 4 equal each other, and 5 and 8 equal each other. So we can put them all together, they are all the same angle. Maybe I'll use a black line, a single black line like this. And then the double black line. Angle 2 equals angle 3 equals angle 6 equals angle 7. They teach these as a bunch of different rules, but that is exactly what it boils down to. Angles that are the angles opposite each other, they come in pairs and they kind of line up. They're the same value. Same with the other two sets of pairs. So if I were to redraw this and if I were to redraw this, I'm assuming those are the same, those are parallel. I could just as easily call this angle A, angle A, angle A, angle A. And this is angle B, angle B, angle B, angle B. They're all the same value. They have there's more rules. I only stop with the first two, but the rest of them all say the same shit. Alternate interior angles are equal. This is the rule number 3. I'm gonna put a boxer on this. This is pretty important. This is the big picture. That's the big picture. Rule number 3 is alternate interior angles. Like 3 and 6, and 4 and 5 are equal. But that's just for putting these two together. They just added more terminology to go with it. They made this all really fucking hard to learn when I was in high school. There's a lot of shit going on. I'm like, how do I keep track of all that? Well, if you redraw it, there are only 2 angles measured. And once you know one of them, all I need to know is a single angle and we can find all the rest. Because, let me finish the other equal. What? All the way around is 360, or you just do A and B have to add up to 180. No matter which way I look at it, A and B make a 180-degree circle. So they do the alternate interior angles. They say the same thing about alternate exterior angles. Are equal. And that's angle 1 equals angle 8, and angle 2 equals angle 7. But we could have pulled that all from right in the beginning. Just out of the first 2 rules, combining what we knew. And they have a lot of weird jargon for the way to describe this. Like they describe these 2 lines as the interior angles on the same side, or the exterior angles on the same side. I think it's just easier to say that 2 adjacent angles are supplemental. And going off the picture here, that just means any combination of A plus B equals 180. All right. You guys ready for more? This is going to have more math again. We're back to doing some math. That's a lot of terminology. And the most you had to do there was subtract 90, a number from 90, or subtract a number from 180. That's a big time, no math done in an hour and 15 minutes, or an hour, basically. So there are 360 degrees in one circle or one revolution. Or a full rotation. And draw the clock real quick. But I'm going to have lines connected to the numbers. I don't know that this is in this section, but it's got to be in the section coming up. So this is 12, 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12. Let's say I made it a clock. So it's a circle. There are 12 sections here. So 360 degrees divided by the 12 different sections equals 30. Each little wedge on this is 30 degrees. But you know, when the hand is moving along, it's like the minute hand, it ticks minute to minute. Oh, that's fun. That's interesting. So each section here is broken up into 5 minutes, right? I'm going to call them time minutes because we're about to use minutes in another way as well. That makes there's 30 degrees for 5 time minutes. Which makes each time minute 6 degrees. Which makes it so you can really get a feel for how small a degree is. So if you like look at like 12 o'clock and 12:01, that's a fucking sliver. That's like a very, very small, hard to see amount of time on the clock. And it's got 6 degrees in it. And yet degrees get broken down into smaller pieces. We could have half a degree, 1/8 of a degree, etc. So they break down the terminology a little bit more. 1 degree equals 60 minutes. And they use a single apostrophe. 1 minute equals 60 seconds. And here they use 2 apostrophes to note it. Which is terrible. They know clearly whoever came up with the clock and whoever came up with this notation system had degrees and minutes. They use the same words in this throughout them both, but they mean different things entirely. Other than like 1 minute is 60 seconds, that correlates to time as well. But if we look at this right here, if we stack it up, 60 minutes is going to equal 3,600 seconds. Or another way of writing that is saying 1 degree equals 3,600 minutes or seconds. You know, I'll be honest with you, I really don't know what the fucking point is with the minutes and the seconds. Because we're going to show you how right now how to convert it back to a decimal and then how to convert it back to minutes and seconds in terms of this degree shit. But like when you look at it, you're gonna be like, nope, that shit's meaningless. That means 0 to me. I don't even know what it's good for. So let's take a look at switching back and forth between them. I'm going to leave that out there because we're going to reference that. So if you want to write, so degrees tend to be listed as you have XXX degrees, YY minutes, ZZ seconds. That's like the general notation. Now, see, these may be smaller, like why, you may only have 7 minutes, so you wouldn't, you might put 07, or you might just put 7. I only wrote XXX because you could have over 100 degrees. In fact, since it goes up to 360, most degrees are over 100 degrees. But normally we want to just write it as XXX with some decimal value. So how do we do that? Well, we can take this, and to convert that way, we take XXX, the degree part, and we add the YY minutes divided by 60 minutes. And we add the ZZ seconds divided by 3,600 seconds. Which comes from these relationships right here. Let me give you an example so it's a little bit more meaningful. Because I'm sure that's just a bunch of, it's a bunch of horse shit, right? Let's say we had 125 degrees, 22 minutes. And is that what I want to use? Now let's go 40 minutes. I'd rather use the values I already got written down. And 15 seconds. If I want to write this as a decimal, I can do this as 125 plus 40 divided by 60 plus 15 divided by 3,600. Just throw it all in a calculator, do it all at once. If you do put it straight in, 125 plus 40 divided by 60 plus 15 divided by 3,600. If you do it in that order, you're good. You don't need to worry about parentheses. Everything's good. You should get 125.6708333. Or about 125.671 degrees. Now, seeing as how each minute on the clock is actually 6 full degrees, I need to break that in like a single minute into 6 parts to get 1 degree. I can't even fucking draw a degree with a pencil because the pencil's too fucking thick. And I don't know how to draw an angle that small. 1 degree is so small. So I don't know what this shit's good for, other than like, if you're aiming for like, I don't know, military shit and you're firing a missile, and you're launching from, I don't know, an Air Force or a military base in California, and you're trying to hit somewhere in Europe, or let's say Russia. Russia likes causing problems, so like being off, it's so far away that by being off just a half a degree, you're going to hit a completely wrong target. So. If the thing
You
that,
have to calculate time and.
yeah, there's a lot more going on because the Earth is rotating. There's a lot more going on with it, but if none of that mattered, even just like trying to hit a target with no physics getting in the way.
The wind.
Yeah, no wind, yeah, because the wind is gonna cause, disturbance, shit like that too. Avoiding all fucking anything like that, still hitting something that's 1,000 miles away, even if I'm off by just 0.01 of a degree, I'm gonna miss by a long, long, long shot when it gets to the target. But they came up with this shit long before there was intercontinental ballistic missiles. So what were they using it for? I don't know. Maybe sailing, like heading from, I don't know, fucking one of the bays in Spain to Colombia, or the new world required a specific angle. Even then, that's not gonna work because the fucking tides in the wind. I don't know where it came up. It doesn't seem helpful to me. But in both cases, that's how you do it. What about going the other direction? About the other way. Which seems to me to be the less useful method. So let's say we start off with 25 degrees and 25.375 degrees. Okay, first thing you do is you peel off the degrees. Put them on the side. We will definitely have 25 degrees. And multiply the remainder by 60. The remainder is the decimal. So just take the entire decimal and multiply by 60. Times 60 is 22.5. The whole number here is minutes. And we'll peel it off. (25 degrees), 22 minutes. And we will take the remainder and multiply again by 60. I spelled that backwards. The remainder is 0.5. And if I multiply it by 60, I get 30. These are my seconds. So those two things are equal. What?
I said, okay.
This is more meaningful to me, other than I know it's less than a half of a degree. Here, if I think about it, I know it's less than a half a degree, but here I can actually see it relatively clearly. It's not, it's below 25.5, so it's below the halfway mark. But even then, in a trade school or something like that, 1 degree is really fucking small. So, like that's when you need some, you're dealing with something that's long and you need precision on the angle that you're building it at. Like super precision, like, again, still, I don't, even if like the instruments you use, if they use different things to measure this shit. There is the protractor. Protractor measures angles. Again, we try to spell it the correct way. And they also have that stupid thing that's got a point and a pencil. The compass. Those can be used to measure angles also. None of those measure minutes or seconds. So, like, not reliably. But that's it for 17.1. I don't know that starting 17.2 is helpful for you guys right now. It's on parallel or shapes. I guess we could. Let's start the shapes and talk about what their names are. We all know the rectangles. We tend to call sides that are opposite each other, they have the same value. We call one of them length. And the other side that are opposites width. So some words to know for this stuff is perimeter means distance around a shape. And area is a measure of the space enclosed. This is true for all those things we're going to do. Those kind of like ideas. For a rectangle, the perimeter, we usually use P for perimeter and A for area. One way to do it is just start at a corner and go around the object. L plus W plus another L plus another W. So if I were to rewrite that as a formula to memorize, there is 2L plus 2W. The area is usually a multiplication thing. In fact, I can't think of one where it's not. For a rectangle, it's length times width. And so you can either have the dot in there or don't have the dot. Oftentimes they don't put the dot. So this is for rectangle.
What about
What?
volume?
Volume is 3D shape, like a box. That would have height. And perimeter becomes a little bit meaningless there. Surface area is there. Volume is just multiplying by the height. So I don't know that we go into it in this section, but volume of a 3D rectangle or a box, length times width times height. I've got L going down that side, I've got W going there, and I got H going here. That is pretty useful to know. I don't know why they didn't include it. That's just useful to realize. Like how much volume you want to mail something. You know how many square cubic inches you've got of shit you can mail.
When do you use the pi on the circle?
That's coming up in like 17.3. It's coming up. Circle is the one shape we're not doing in 17.2. Circle has its own fucking special, it's its own thing. But it is coming. What is a rectangle that has equal sides? With a square. So a subset of the rectangles is the square. Square is a rectangle with equal sides. And we tend to use S for these, for side. Perimeter here, if we add up the sides, you will see there are 4 sides, so 4s. So it's really just s plus s plus s plus s. The area is side times side for s squared. I meant to do that in green. So the area of a square is as. A equals SS. Good stuff. Same thing with the volume of a cube here. A 3-dimensional cube is just multiplying by the height again, but the height has the same length as another s. So volume here would be s cubed. 3D. The rest we're not going to do 3D on because there's just too many shapes implied by what we could do. As you see. Something that's similar to a rectangle, but slightly askewed. A skewed rectangle is called a parallelogram. They tend to call the bottom here, bottom and top B. The sides are S. And what they do is, if it's not given to you and you know some trigonometry, you can find this value, but you need this vertical distance between the two parallel lines like that. We need that. That's called the height. So B is for base. S is for side. And H is for height. The perimeter, we can see if we add it up, we've got B plus S plus B plus S. We just go around the edge. But that just condenses down to 2B plus 2S. The area is B times H. You're like, what? How's it happen? It's basically like the same. It comes from the idea of a rectangle. If I were to pick up this piece right here and move it over here and do that, I now have a rectangle that's got a length of base and a width of H. So that's where that formula comes from. Just like a rectangle, when we skew it makes a parallelogram. The subset of rectangles, the square, when we skew a square. Yeah, I should put this on the page. The skewed square is called a rhombus. So it's like a parallelogram, but all 4 sides are equal. So it's a parallelogram with equal sides. Just like with the parallelogram, we mention a vertical height between these two. H. The perimeter we can see if we add up the four sides is 4S. And the area, instead of being base times height, is S times height. Are we having fun? The trapezoid. Okay, this is where shit starts to change. B1, B2, call that A and C. And again, we need a vertical distance here. So H.
So A and C don't measure the same.
They don't have to measure the same. They can be different. Usually when you see them drawn, they're not. They're not, we tend to not use trapezoids, not the same shape. We actually use trapezoids when, you know, like building a barn, as we'll see in a second. Trapezoids do come in. The perimeter here, there's no shorthand notation in this. It's A plus B1 plus B2 plus C. Now, the idea of the area comes from taking the average of the two bases. So add them up and divide by 2 or multiply by 1/2. And then multiply by that H.
You add B1 plus B2 and then you divide it by 2.
Yeah. All right, so all of these. What do I want to call them? These are all polygons. Polygons are shapes with a countable number of sides. All the ones we've just done, all the above are called quadrilaterals. Because they have 4 sides. And I even think lateral means a side. But there's another shape we use almost as much as we use the circle. That is not a quadrilateral. And that is our beloved triangle. They come in a variety of flavors. I have a B on the bottom. Even a good old right triangle meets this. To get the area, we're gonna need the height. In a triangle that looks like this, it's that. In this triangle where we have an angle that's way bigger than 90, we drop it down like that, and we call that H. You kind of like, you extend this line out, and then you figure out how far it is from that top. That top point is called the apex. That's an apex too, right there. The top point is the apex. And on the right triangle, A equals H for the right triangle. Perimeter in all of them is A plus B plus C. There are a few ways, couple ways to calculate area. Area, when you've got it, is 1/2 base times height if you have the height. This very much requires having the height. If you don't have height, we use Heron's formula. Heron's formula is A equals the square root, and this is a big thing, S times S minus A times S minus B times S minus C. Where S equals 1/2 of A plus B plus C. Or if you've already added up the perimeter, it's 1/2 the perimeter. Now, this looks super fucking complicated, right? Finding S is super easy. You add up the sides and you divide by 2. And then you just take that, give that value and you go, I have that value, and then I subtract each side from it one at a time to find the other 3 things. You multiply them all together and take square root. Mathematically, it's super easy. Remembering the formula is a pain in the ass. Well. I think I'm going to save examples for Monday. And we'll do 17.3 on Monday. Let's call that a wrap. Recording.